Hi there, welcome to another vintage computer video. What I'm holding here is my latest project. It is a single board computer. If you look closely, it's not actually a single board, it's actually two boards. The front board is the display board and the actual single board computer is the board on the back. Now this front board is actually repurposed from a prior project. This was the display board off of my 8008 single board computer. So a few years ago I did a video on the 8008 microprocessor, the world's first commercially produced 8-bit microprocessor. I built the single board computer for that. I had built the display board for it. I ran a little monitor on the display board. I probably did some other demos with it. You can go back and watch my 8008 video sometime. It was, I think it was one of my funner videos. But I decided to go a little bit older this time. Flipping it around, we have another very small CPU. This is not an 8008, this is a 4004. Now the 4004 has the distinction of being the world's first microprocessor. Now the 8008 was the first 8-bit microprocessor. The 4004 preceded the 8008 and it is a 4-bit microprocessor. Now you might think you can't do a whole lot with 4 bits, but you can actually do quite a bit. And you will see me run some demos on this and a monitor program and actually run a calculator on it. One of the first applications for the 4004 CPU was a calculator made by BusyCom. You can actually find a few of those around sitting in museums. They tend to go for a lot of money on the private market, but you can probably find one in a museum, and you would have found your 4004 in a BusyCom calculator. So this 4004 here, this is I think this is the purple ceramic and gold one. So this video, I'll start out with showing where I harvested this 4004 microprocessor from. You can buy them on eBay. They tend to be very expensive on eBay. I was lucky that I was able to acquire a piece of equipment that had a 4004 in it already, and I borrowed the 4004, used it to my project, and when I'm done with this, it'll go back in that piece of equipment, and I'll do a video on that too. Now, as I may have mentioned, one of the applications for this was the BusyCom calculator, and I will demo in this video, one of the reasons I have my front panel on here is I will demo a calculator. Because it seems only fitting if this thing saw its genesis with that calculator that we actually build a 4-bit calculator. So anyway, let's get started with the 4004. Okay, let's see what's inside this briefcase looking thing here. Open it up. And what we have here is a Prolog M900 PROM programmer. With manuals, all kinds of good stuff here. So I recently picked this up on eBay, not because I need yet another PROM programmer. I've got lots of those of various styles, but because this M900 should have an Intel 4004 CPU inside of it. And I have a project where I want to use the 4004, so I'm going to crack this thing open and see if I can borrow the CPU out of it. Then we'll have some fun with that in the video, and then when we're done, we will put the CPU back in this, and in a future video we'll do a video on the M900 itself. This thing is huge. It's a behemoth here. It's got modules that plug in and out. You swap it out, you can put in different modules for programming different PROMs. I don't know exactly how to tear this thing apart, but I think I can just yank the programmer itself out of the case, and I'm going to have to figure out how to get inside of this contraption. Okay, let's take a look. So right here is our INS 4004D, that's our CPU. We've got some 4002-1, those are both RAM chips. 400-8 and 9, those are for interfacing with the ROM, so those will go with these 3 ROM chips here, then probably have the programming for this. Okay, so all I need to do is just pull this thing out of its socket. There we go. I know I just got some anti-static foam there. There's our 4004. Okay, one thing I wanted to mention is Jim loses 4004 single board computer project. So just like Jim was the inspiration for my 8008, he was also the inspiration for my 4004, and you can look at his website, and he's got lots of information. He's got one he built here on a breadboard, and he's got all of the schematics for it. Good starting. He's even got a power supply there. A good starting point. And he also wrote the firmware that I am going to base my firmware off of. So again, a big thank you to Jim for publishing his project, which made my project even more feasible. Okay, let's take a quick look at the schematics. Now, I'm going to go through this really fast because people can always go look at the schematics in detail later. Now, this first page here has the basic 4004 and 4040 chipset and support. So you've got the clock chip here, the 4201, along with its crystal, its reset circuit. There's a little capacitor resistor thing here that does the startup delay on the power on reset. Out of it comes a reset line, which goes into here, into the 4040 CPU. Down here's my 4004 footprint. It's in parallel with the 4040, so either of these footprints can be used. And the reset line kind of needs to hook up to all of the vintage devices. They all have that reset. Also, out of the 4201 comes the two clocks, the phase 1 and phase 2 clock, and they also are going to hook to most, if not all, of the vintage devices. So you've got here the 4201, the CPU with both footprints, and the memory interface. This is the 4289. This lets us use any standard memory device, any standard 8-bit memory device with our vintage 4004 or 4040 CPU. The data bus for the 4040 and the 4004 is, of course, 4 bits. So there's only D0 through D3. And you'll see it hooked up to here, but you're going to see this on other pages come through as well. So they go in here. This chip does some magic to actually get you something that looks like an 8-bit interface to your standard memories. I've got a little bit of junk over here for the reset signal because I wanted a TTL level reset signal. I've got a little bit of junk over here for handling interrupts, even though I haven't done anything with interrupts because the 4004 does not support them. The 4040 does, but not the 04. And then here we have a PLD that implements a bunch of miscellaneous logic. Nothing super fancy in here. It's mostly just ands and ors. But to reduce chip count, I stick as much of it PLD as I can. And something here that is address selector for the onboard peripherals. Page 2 is the power supply. So we've got the two 5-volt DC-DC converters. You can hook them you can either use 5 to 5. These are isolated, so you can get -5 on the other side, but you can use 5 to 5, or you can use the power jack and do like a 12 to 5. The prototype you're seeing in this video, I did 12 to 5 instead of 5 to 5. These things are 2 watts, so they're good to about 400 milliamps each, and they're in series to give you the 10 volts. Then we've also got this 7805 footprint, so you can supply the whole thing with a 12-volt jack and get your 7805 to down kick it to 5 volts. Fuse in here I put here because I actually killed a DC-DC converter by overloading it once. You'll see these TVS diodes on any project that's using super expensive chips. I usually put those in because they will protect against transients. They'll also protect against screw-ups. If you put way too much voltage on, the TVS will shunt it down to ground, and you'll probably blow a fuse rather than obliterating a vintage chip. Page 3 is our memory. So we've got a big socket here, a 32-pin socket that can support devices all the way up to 39SF010 if I want. Header that lets me select different things. I mean, you can use a 28256 if you want, 27512, or something like the 39SF010. Now, I built in a memory mapper, and I do this with a lot of my projects. I started doing this with some of the RC 2014, the Z80 stuff with CPM, that it's often useful to have a larger address space than the chip supports. With Z80, we would take the 64K address space and expand it out to 256 or a megabyte or something. With this 4004, I've taken the 4K address space and extended it out to about 16K. This is, I don't know if the chip identifier is on here, but this is a 74 HCT 670, which is a 4x4 register file. Basically, what we do is it takes a 2-bit address in here and a 2-bit address in there. One of these is the write address, one of these is the read address. When a read comes in, it's taking the top two address bits from the 4K space, the A10 and A11, and that will cause it to pull a file out of this register file and put it on the 10, 11, 12, and 13 address lines. So that is how I took a 12-bit address and I turned it into a 14-bit address so that we can address 16 kilobytes of RAM. And we can do it in 1K pages if you wanted to get fancy and keep some pages from one bank and some from another. I'm not going to go through all the details of how this thing works, but these little memory mappers are easy to do and they use a standard TTL chip. Page 4 is all of the serial stuff. So down here I have an 8251. This is one serial option. We've got a crystal divider to get baud rates in the 8251. You could use this and have a UART. UARTs are nice because you don't have to bog your CPU down doing serial stuff. You can just write to ports, and then the UART will handle putting it out on the serial for communication with your host computer. So the 8251 is one option to do that. I'll talk about how we talk to it in 8-bit in a subsequent page. And the other option is over here. I got this from Jim Luce on his project. This is a bitbang serial interface using one of the output bits from one of the RAMs. It uses one output bit, and then over here it has one input bit, the test line on the CPU. And this is being bitbang. What that means is the CPU sits there and individually sends each bit out on the serial port. That's very CPU intensive to do that. You have to kind of stop everything else you're doing and talk on the serial. Then we've also got 4 LEDs here hooked up to one of the output ports on one of the RAMs. We'll see the RAMs in a moment. And then we've got 4 dip switches hooked up to an input port that's going to go to our 8-bit RC2014 bus. Let's go over there next. So here is my 8-bit RC2014 bus. So I choose the RC2014 bus because it's a very common bus. And I got started with my recent resurgence in vintage computing projects with the RC2014. So I have a ton of RC2014 cards. So the RC2014 bus, it's a standard 8-bit bus. It's got up to 16 address lines. It's got 8 data lines. And it's got read and write strobes. And it's got like an IO request bit here. So how are we going to hook this up to the 4004, which 4-bit CPU? Well, we will use this 4265 chip. And the 4265 takes the 4-bit 4004 bus over here on this side. And then on this side, it gives you 4 different 4-bit ports. And there are at least 13 modes that you can configure those ports in. I'm using mode 12, which gives you an 8-bit address bus, which we can see here buffered and go out to the 8 address lines of the RC2014, as well as a 4-bit data bus and a read and a write strobe. So those read and write strobes can go right on out there to the RC2014 bus. The data bus I need to do a little bit of extra work with because it's only a 4-bit bus and I need 8 bits for my RC2014. So what I'll use is a combination of bus transceivers and latches. And what we will do is we will use the latches for the upper bits. So if you want to write an 8-bit value, first what we'll do is we'll have you write and latch the upper nibble, and then you write the lower nibble, and it will put out the lower 4 bits as well as what was latched down here with the upper 8 bits. Similarly, when you want to read, we can read the lower nibble coming in this way. And then when we do that read, we will latch the upper nibble, and then we can come in later and read the upper nibble. So we kind of have to do an 8-bit bus transfer in 2 data operations because we have a 4-bit CPU. But this gives us an 8-bit bus. We can use that for our 8251 UART. We can use it to talk to our switches and other stuff. We can use it to talk to RC2014 backplane. We use it to talk to all those 8-bit peripherals. Page 6 are the RAM chips. So these RAM chips are 320 bits each. Usually you use them in pairs. You can see one piece of the pair here has this P0 pulled up. The other has the P0 pulled down. That controls some of the internal addressing. They, of course, are hooked up to the 4-bit data bus. There's a sync line. There's a RAM select. The CPU actually has 4 RAM selects, so that can give us 4 banks. Each one of these has an I/O port associated with it. So I followed on what Jim did in his project, and I hooked the BitBang serial up to this I/O port, and I hooked the LEDs up to this I/O port. Kind of weird that your RAM has I/O ports built in it, but must have made sense at the time. Finally, page 7 is a multi-module connector. Now, multi-modules are something that came a little bit later in the early computer days. These actually came with multi-bus, and they came about the time that the 8080 CPU became popular. Now, I use the multi-module sockets because I've been doing a lot of multi-bus stuff lately, and I built a lot of these little multi-modules that just kind of piggyback on top of the board. You'll see me when I do the demo, you'll see me use a couple of these. I've got a speech synthesizer one. Okay, I'm going to take a very quick look at the PC board. So here we have the CPU. The 4004 CPU, it's a 16-pin device plugged into a socket. You'll notice there's this bigger socket that surrounds it. That allows us to use, if we want, instead of the 4004, we can use the much cheaper 4040, which you can find on eBay for like around 60 bucks if you're lucky. Next to it, we have a clock driver chip, a 4201 clock driver chip along with its crystal. 2 RAM devices. These are 4002-1 RAMs. I included sockets for putting an additional 6 RAM devices if you wanted to. Over here we have the 4289 standard memory interface. So we can interface it to a normal memory device, which you can see I've got a zip socket here, with a 39SF010 flash device. So it actually supports several different devices you can plug into there. This is one that's convenient for me. It programs really fast. You can interface 4 kilobytes of memory with the 4289. Here we have the 4265, which is a peripheral interface. So you can use it. It has 4 4-bit I/O ports that it can configure in a variety of different modes. And one of the things that we will use that to interface with is this connector here, which is an RC2014 compatible bus connector. It only does the I/O bus, doesn't do the memory, because again, this thing only does 4K of memory. There's not much sense in hooking memory up to the bus. Let's round out this section of the board over here. We have some DC-DC converters, because this, all of these vintage chips, the 4004, the RAMs, the memory controller, and the peripheral controller, they all need both +5 and -10 volts. So these here are 5-volt isolated DC-DC converters, each of them 2 watts. If we put them in series, we will get 10 volts, and because it's isolated, we can make it -10 volts. Now for our +5 volt supply, I have a footprint here on the board for a 7805 regulator. 7805 is good to about 1.5 amps with a heatsink. I need at least 2.5 amps because it also powers the display board. And the display board just guzzles electricity for these drivers and these 7-segment displays. This display board itself takes like 1.5 amps. It would totally max out a 7805. So what I put in here, I put an Easy SBC regulator. So Easy SBC, they make these little switchers compatible with the 7805 footprint. This one here is a 3 amp switcher. It's just soldered right in there in place of 7805. If you wanted to go pure vintage, you could just dispense with the display board. You could put a 7805, and a 7805 would run everything on this board itself just fine. Now let's look at the left side of the board. So here we have a multi-module connector. This is an example multi-module. It has a little connector out the back. And these became popular in the later, I guess I would call it the later early years. So the multi-bus years started with the 8-bit multi-bus boards like the 8080. This is just a simple, small 8-bit interface, and there's a lot of these boards that you can just plug into that piggyback connector and then give yourself something. Then we have a little bit of logic here that works with the inputs. There's actually a footprint here for a 4-bit dip switch. We've got 4 lights, which are hooked up to one of the I/O ports on the RAMs. Over here we have A serial port, I like DB25s because they seem period accurate from what, early computers used. And the DB25 can be driven in two ways. Now, one way you can do it is with bitbang IO, and I inherited this from Jim Luce from his single board computer. You've got these couple transistors here. So I also have a UART. I have an 8251 UART right here. Got our reset switch. You've got a PLD device here where I just threw a bunch of miscellaneous logic into it to reduce chip count. Barrel jack for power coming in. And I think that's pretty much everything. Okay, let's power on the computer. Turn on the power switch. First thing you saw was a little blink over here on these LEDs. I put that in there as a power on self-test indicator to prove everything's working. That way, even without a serial port, I could just look at it and tell that the CPU and the RAM and everything else worked. So anyway, we're looking at it now. We've got it up on screen here. This monitor I got from Jim Luce from his 4004 project, and the first 9 options are all from his project. So let me push 1. And we will see the LEDs blinking back and forth. Let me push 2, and we get a slightly different pattern of LEDs blinking. 3 is an addition demo. So he got some math routines. He put them in here, and you can add numbers. So I'm going to type 1, 2, 3, and 4, 5, 6, and then it prints out the sum. Let's hit Control C, and then we've got subtraction. Let's do 4, 5, 6. We'll subtract 1, 2, 3 from it. We've got the difference. Multiplication, 1, 2, 3, 4 times 2. Simple. Division, let's do 333 divided by, well, that's not interesting. I guess it is. 333 divided by 111 is 3. Sure enough. Fair enough. And then what else? There's a tic-tac-toe game. So let me pick a position. Let's do, I'll take 5. He's gone there. I'll do 2. He's gone there. I will do 3. And then I'll do 4. Oh, he won. Yeah, he got me. Whoops, I'm not good at tic-tac-toe. There's a number guessing game built in. Let's see. Think of a number. It's actually randomizing while it's waiting for you to the space bar. Then we just do a little binary search here. 50, 75. Let's do 60. Too high. Let's do 55. Too low. 58. Too high. 57. There we go. We've guessed the number. And then display the switch position. So hit 9, and that's hooked up to these 4 switches over here, which are hooked up to the 4265. So if we flip them, we can get various, and it's actually setting the LEDs to the switches that are up. So, various different bits are coming in there, like so. Yeah, see, just playing with the switches. Anyway, let me see if I can exit that. Now the next 4 options are mine. So I put in the capability because I built a bank switcher into this to be able to switch banks. So if we push B, we'll go to bank 2, and bank 2 has my multi-module stuff that I put in here when I was playing with the multi-module socket. So I need to actually plug something into there first. So what we're going to do is we're going to plug in my SPO256A speech synthesizer module. We'll plug that in. I'm going to turn the power off because I don't want to destroy my expensive project. We will plug that speech synthesizer module in. Let's power it up. Bank B. Okay, and let me, we'll do the SPO256A speech multi-module. And I've got 2 different phrases it can say. So I'm going to push this, and the SPO256, it's a phonetic speech synthesizer. It'll start talking. Okay, it's not the loudest thing in the world, so I may have to turn the volume up on that. But let me make it say, I've got another bigger sentence that I programmed into it. This is a single board computer that uses an Intel microprocessor. Okay, the next one we will do here is this Digitalker. So the Digitalker is made by National Semiconductor, and it has a fixed vocabulary, whereas the SPO256 was phonetic, it had unlimited vocabulary. This has a fixed vocabulary, so it can only say certain things. So let's go in again. We'll go Bank B, Digitalker. And the first thing is the phrase is programmed. The 0th word is the phrase, this is Digitalker.
This is Digitalker.
The next one I've had, it'll say like the time is 1:05 p.m. or something, because it's got numbers and letters and stuff like that.
Time is 5:08 p.m.
Next I have a system ready.
System ready.
I like that. I could actually make the computer say that every time it booted up.
System ready. System ready. System ready.
Yeah, I like that one. And the next one, I think this came from a sensophone. Maybe this is something about temperatures.
Hello. The temperature is 72 degrees. Have a good day.
Very nice. One more multi-module to do. Let's pull this out. This one here is one that I built for testing. It's got a bunch of TIL 311 displays on it. So let's power it up. And again, with the Bank B and display multi-module. And that's all it does. It just displays 1, 2, 3, 4, 5, 6 on it. Okay, as I mentioned before, one of the things I implemented here is a calculator. And this is actually the reason for taking my 8008 front panel and sandwiching it on here, because it has a handy numeric keypad and it has a 10-digit display. So what we're going to do here is we use the numbers for the numbers on the calculator. And then A is plus, B is minus, C is times, D is divide, E is equals, and F is clear. Now this calculator that I have programmed into the 4004, it is only an integer calculator. I did not take the time to make it support floating numbers. And it is only a positive number calculator. I did not take the time to implement negative numbers. So we could do that. But this is just kind of for fun, because one of the original uses of the 4004 was in a calculator, so it's only fitting we do a calculator. So let's do 123 plus 456 equals 579. Sure, that sounds about right. Plus 1, 580. Let's take and divide that by 2. We've got 290. Let's multiply it by 3, 870, and then let's subtract 100 from it, 770. So typical calculator stuff. For adding and subtracting, I believe the routines that I used, they will work up to, I think they will actually work up to 16 digits, but I only use 10 digits because that's what's in the display. So let's try adding 4, 5, 6, 7, 8, 9, 0. Okay, so that is a big number. Let's add 5 to it. Why not? There we go. Added 5 to it. Now, multiply and divide do not support as large a number, so I cannot, unfortunately, not divide or multiply this. But anyway, there you have it. There you have a calculator using my front panel display board, and of course, on the back is the 4004 CPU board with the 4004 CPU there. Okay, I hope you enjoyed my video on the Intel 4004 microprocessor and the single board computer that I built to go with it. There he is again, that little tiny chip right there. If you enjoyed it, please do subscribe, please do like the video, share it with your friends. If you used a piece of equipment that had a 4004 back in the day, then please do drop a comment and say what you used a 4004 for. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.